Hi, everybody. Really happy to be here with you today. So, yes, I will be going over some of the high level findings and policy recommendations that stem from this research project. And so, first, I'll give you some background that you don't need on the Great Lakes system because you're all way more expert in it than I am, but just to set the stage. Then I'll go over something that we're more familiar with, which is more on what are the fuels and ships that are operating on the Great Lakes. How much are they emitting? What are the major ports? Um, and then we'll get into some questions on how can the Great Lakes St. Lawrence Seaway system decarbonize? What are the fuels and power options? What are their trade-offs? What are the regulatory considerations related to air pollution, greenhouse gases, and risk and safety? And then I'll end with some conclusions and policy recommendations. We'll have some time for questions at the end. I'll do my best to answer yours that you might have during the webinar. If there's any that I can't answer, I'll take it back to the co-authors and respond afterwards. Toward the end, I'll also put my contact information on the screen. So the Great Lakes St. Lawrence Seaway system, about 2,300 miles, 110 plus ports, and 136 million tons of cargo were transported in the system in 2022, and that was valued at $26 billion. And this is the study area that we were looking at for this report, the Great Lakes and the St. Lawrence Seaway. Within the system, we estimated that in 2021, the ships that were operating on the Great Lakes St. Lawrence Seaway consumed about 500,000 tons of fuel. And this is the distribution by ship type. So ship type is along the bottom. The total amount of fuel consumption is on the y-axis. And we've broken it up between distillate fuels, which is marine gas oil, which is similar to diesel fuel, and then residual fuels in yellow. Residual fuels are high sulfur heavy fuel oil. And when that fuel is used, then the ship is also equipped with an exhaust gas cleaning system um, to reduce the sulfur emissions because the system is in the North American emission control area, which requires lower sulfur fuels to be used than the global limit. There is also a little bit of biodiesel that's being used on the lakes in bulk carriers primarily, and that's indicated in green. The emissions from consuming about 500,000 tons of fuel is about 1.6 million tons of carbon dioxide. And about 75% of that is from ships that are flagged and registered in the United States and Canada. And then the other 25% are from foreign flag ships that come in through the seaway for import and export. If you look on the bottom left pie, that's the US flagged ships. And you can see that 2/3 of the emissions are coming from bulk carriers and then a quarter from tugs. And this includes not only the tugs that are operating in the ports, but also tug barge combinations. On the bottom right hand pie, you're looking at the Canada flagged ships. So half of the emissions are associated with Canada flagged bulk carriers, and then followed by chemical tankers at 16%. And you can see that there's a number of other ship types that are represented here beyond a bit more diverse than what we have for the US flagged ships. We did a port survey, we being primarily GSGP actually, and then ABS made this map. So I'm showing 10 major ports here, and we're showing US ports in red, Canadian ports in the blue stars, and then whether or not they have onshore power supply, shore power, which is represented by the plugs, and then if they have any alternative fuel infrastructure. So you can see it's pretty sparse. There are a few plugs on the screen. You've got Duluth, Milwaukee, Chicago, and Montreal. And of those four, only Montreal has a high voltage onshore power supply system. And the high voltage is what you need for cargo ships and cruise ships. And so Montreal has that ability. They have shore power for cruise ships. Other ships can winter over there and plug in. And then for Duluth, Milwaukee, and Chicago, these are low voltage, like 480-volt systems that you can use for smaller ships, like hovercraft, tugs, pilot boats, but they're not designed for things like big bulk carriers or chemical tankers to plug in. So as you'll see later, this is an opportunity for expanding onshore power supply to provide electricity for tugs, hovercraft, but then also um, to provide some high voltage systems as well that cargo ships can use. Quebec City is the only place in the lakes where we have an alternative fuel supply, and this is in the form of LNG, liquefied natural gas. And the rest don't have any. They have fuel supplies like diesel, for example, propane, even at some places like Chicago, um, but no alternative fuel infrastructure, which is something that we're going to need if we're going to use fuels apart from diesel fuel and LNG, but also things like methanol, ammonia, and hydrogen, which are some fuels that we'll talk about a little bit later on. So the big question that we were trying to answer is how can Great Lakes St. Lawrence Seaway shipping decarbonize? And we looked at a number of different options. So these are the fuel options that we examined, and they can be used in engines, fuel cells, and for electricity batteries. So there's fossil-based fuels, and those would include methanol, ammonia, hydrogen, and dimethyl ether, DME. We have biofuels that also can be methanol. You can make diesel, biodiesel. You can make methane, so biomethane, and you can use that as natural gas or even liquefy it for liquefied natural gas, and also DME again. And then we have e-fuels. So this is where you use electricity to make hydrogen, and then you use captured carbon if the fuel requires carbon, like methanol, diesel, methane. Um, Otherwise, you're using the hydrogen for all of these fuels, but only the hydrogen for ammonia and for hydrogen, pardon me. And then we looked at electricity. So we looked at the potential to use batteries um, for battery electric cargo ships and tugs and hovercraft, or otherwise use it as a hybrid energy source for cargo ships. So we looked at these fuels and the propulsion technologies and combined them together. So we had this gigantic matrix of different fuel options, different power options. Right now, all of the ships are using internal combustion engines, very common, and there's not much yet in the way of battery power or fuel cells. There's nothing that we know of that's using fuel cells on the lakes, and only a few demonstrations worldwide, for example. So we looked at these different fuel and power combinations, and we examined their life cycle greenhouse gas emissions. And I'm going to show you some charts that are going to show you the differences in those life cycle emissions um, next. Total cost of ownership. This includes how you have to change the equipment on board the ship, like the engine, the fuel tanks, the fuel supply, if you're going to put in a fuel cell, if you're going to put in batteries, and then also the operational expenses, including how much does it cost for the fuel. And then for fuels where we have really no infrastructure, like hydrogen, for example, or expanding electricity so that way you could use batteries, there's an additional cost of um, building out that infrastructure that's included in these costs. Applicability, which is can this fuel and engine or power combination be used on the types of voyages that Great Lakes and St. Lawrence Seaway ships are performing? Technological maturity. compatibility with existing ships and engines. So there are some fuels that are just a drop-in replacement for the fossil fuel. There are other fuels that require um, changing how the engine is made, changing the fuel systems, or maybe even going to a completely new propulsion system like fuel cells, or doing something like battery electric. Feedstock availability. This is mostly important for biosources, so for biofuels. How much of, there's a wide variety of biofuel options, and they all have very different life cycle greenhouse gas emissions, and that will depend. Which one you pick depends not only on the cost but also how much of the underlying feedstock that you would use to make the fuel is available. And then the risks. This is a topic that is coming up more and more now as we look towards alternatives to diesel fuel in the form of hydrogen and ammonia as some of the leading alternatives. And those come with new risks and environmental concerns that need to be um, considered. I'm going to walk you through these slides. The next four slides are going to have a similar chart on each of them. So we had, before I showed you fossil-based fuels, biofuels, e-fuels, and electricity. So that's how these next four slides are organized. And the chart here is showing the life cycle greenhouse gas emissions for different fuel options. And I've highlighted in the red block the fossil-based fuels. So at the very top of the chart, you have ammonia made from natural gas, dimethyl ether, and methanol, all of these made from natural gas. And then at the very bottom, liquid hydrogen made from natural gas. The dashed red vertical line is the life cycle emissions of the distillate fuel that is most commonly used on the Great Lakes, which is called marine gas oil, MGO. And so anything to the left of that line means that the fuel has lower life cycle emissions, and to the right means that it has higher. So you can see that the main problem with using fossil-based fuels is that you don't get any life cycle emissions reduction benefits. The best you can hope for is something equivalent to marine gas oil um, with methanol. But then if you look at DME, dimethyl ether, um, and hydrogen, you start getting higher and higher, and then ammonia is the highest in this case. The main benefit is that the fossil-based fuels, because they're using fossil fuel as a feedstock, um, are relatively inexpensive compared to the other fuels. So this is where some of these trade-offs come in. Next, biofuels, and I'll walk you through this one again as well because there's kind of a lot going on here. So um, those that are so we have. Let me start with the top one, biodiesel, the top green block here. So this is biodiesel made from soybeans, and the um, brown component of the bar are the well-to-wake greenhouse gas emissions. So well-to-wake is our term for life cycle, how much you emit while you're producing and then using the fuel. And then the blue portion of these bars is the indirect land use change emissions. An indirect land use change is we try to quantify how much the emissions are associated with using things like um, food-based feedstocks like soybeans, and how much that affects the total emissions that you would expect from using that fuel. Because when you're using food as a feedstock, then you need to use additional land to keep up with demand for food and feed for humans and animals. So that's what that blue bar is meant to represent. You'll see that there are some lower on that are negative, and that's when you're using waste materials. And then also if you're using energy crops like miscanthus, which grows on marginal land that otherwise wouldn't be productive, you actually have quite a bit of negative land use change consequences. The main problems with the biofuels is this indirect land use change issue for some of the more popular options and some of the more mature options like biodiesel made from soy. And it's also when you start getting into the biofuels that are advanced biofuels, which are things like Fischer-Tropsch diesel, FT diesel, um, those are quite expensive. And so you have this trade-off between the less expensive biofuels have higher life cycle emissions um, relative to the more expensive advanced biofuels that have low or even negative life cycle emissions. Um, but the benefits here are that these fuels are some of these are drop-in fuels. So all the ones that are in the green blocks, you can fuel up an existing ship with this fuel, and you shouldn't expect any issues. So that's a benefit, and it can achieve low life cycle emissions. And in some of these um, really low life cycle emissions, like Fischer-Tropsch diesel made from miscanthus, or dimethyl ether made from miscanthus. All right, we're on to e-fuels. So e-fuels, these are the fuels that are made using electricity. And the top block in red are fuels that are made using grid electricity. And this is not a very efficient use of electricity, and it results in large life cycle emissions. So you can see that all of them are well beyond the dashed red line. And this is even going out to 2030 and 2050 with the expected grid mix um, for the Great Lakes region. So we have high emissions, and all are also quite expensive at the same time. So you sort of have a double whammy here with the e-fuels, especially those that are made using grid electricity. The bottom green block are fuels that are made using additional renewable electricity. And the main benefit here is that you can get very low life cycle emissions. The the important part here is that this is additional renewable electricity. So anytime you have a new off-taker of renewable electricity, it's really important that it's not taking existing renewable electricity away from another purpose, because then you just need more fossil, use more fossil fuels to make electricity to keep up with the total demand. So additionality is the key word here that we're looking for. Last one is electricity, and this is using batteries. The issue is that the total cost of ownership of using electricity is expensive, and some of this is the batteries. Some of it is the um, building out the infrastructure that we would need in the Great Lakes and Great Lakes ports to enable rapid recharging um, for ships and for harbor craft. And you also don't get um, really get kind of mediocre emissions savings, and these savings are really based on the fact that the batteries with the electric motors are more efficient than internal combustion engines. So you get about halfway, about half as much emissions as you would with using an internal combustion engine and a fossil fuel like marine gas oil. But it's not really enough to get all the way to net zero or decarbonize. You can get to zero emissions if you use additional renewable electricity, which is the top box in green. And so that's what we would really need from a climate perspective in order to um, have electricity as a decarbonization solution. I have a few more slides for you. I'll touch on the regulatory considerations, and then we'll start to go into the conclusions and policy recommendations. So we looked at three different sets of regulations, three categories: air pollution, greenhouse gases, and safety. On the air pollution side, the good news is that all of these alternative fuel and power options can easily comply with air pollution regulations. In the shipping sector, we regulate the sulfur content of marine fuel, which is meant to reduce air pollution in the form of sulfur oxides and then also particulate matter. And we also regulate nitrogen oxides, NOx, which is an air pollutant. And then for the smaller engines, we're also regulating things like carbon monoxide. And we don't foresee any issues with any of these fuel or power options to comply with these existing regulations, both those that are issued by the International Maritime Organization and then those in the US and Canada. On the greenhouse gas side, it gets more complicated for two reasons. The first reason is that the regulations on greenhouse gases aren't really fully developed yet. At the international level, which apply to the large ships on the Great Lakes, we have carbon dioxide intensity standards for new build ships. So they have to be less carbon intense over time. Ships are pretty easily complying with those, and so there's not really any issue with that. Um, the issue more is on what are regulations on the operational greenhouse gas intensity or operational greenhouse gas emissions going to look like. So the design standards, we think, it's able to be accomplished. But the in-use standards, when they are developed, um, are a big question mark because depending on the fuel and in some cases the engine that you're using, the life cycle emissions will be different. So one example is using LNG as a marine fuel. There's a component of the LNG, which is mostly methane, that is going to escape out of the engine, and we call it methane slip. The amount of methane slip is different depending on which engine technology you use. So, when you're calculating the total greenhouse gas emissions of using LNG as a marine fuel, it will differ depending on not only how the LNG was made, but also what engine it's being used in. So, at the international level, the International Maritime Organization is developing a greenhouse gas fuel standard. It will progressively lower the maximum allowable greenhouse gas intensity of the fuels that ships use. And there's also going to be an economic element, as they're calling it. That economic element is not yet decided what it'll be, but it'll be some form of greenhouse gas pricing. So it might look like a straight levy on greenhouse gas emissions. It might be something more like a cap and trade system. It might be something like penalties for not complying with the greenhouse gas fuel standard and rewards for over complying. So that is all still up in the air. And then in the Great Lakes itself, in the US and Canada side, we don't have anything that's going to regulate the greenhouse gas emissions um, beyond what might be developed at the International Maritime Organization at this time. On the safety side, this is challenging for some of the new fuels. So for hydrogen, there's an explosion risk, and for ammonia, the main issue is acute toxicity. If there's any leak of ammonia, then it's acutely toxic to the crew. If there's a leak of ammonia near a port, near populated areas, it's a huge health risk for those that are living nearby. And then if there's a spill of ammonia in the lakes, it's also a toxicity risk for fish and wildlife. So these are some of the issues that are still being ironed out. There's quite a lot of work going on at the International Maritime Organization to develop safety standards, but the key thing to remember is that anything that comes out of the International Maritime Organization is being negotiated by all of the IMO member states, and I think there's 175-ish right now and maybe 90 or so that are active on the environment side. And so trying to negotiate what those standards are going to be globally ends up with the lowest common denominator, if you want to call it that. And then individual countries may decide to go um, beyond those minimum standards. So think of them as minimums, and then the U.S. and Canada could also decide to do something additional on top of that. That goes for air pollution. So there's additional regulations in the US, like internationally, we don't regulate carbon monoxide, for example. Um, could be the same thing for greenhouse gases and maybe even more likely on the safety side. Okay, I have two more slides for you, conclusions and policy recommendations. So, in our study, we broke the conclusions up into those related to fuel and power options, and then those related to regulations, and then we have some policy recommendations. So, for the fuel and power options, avoid fossil-based fuels, and this is primarily because of the large life cycle greenhouse gas emissions, despite the fact that they're less expensive. Use waste-derived biofuels. This is to have the maximum greenhouse gas reduction potential, but keep in mind that these fuels have limited supply of the feedstock, and also all of the fuels that have the advanced biofuels that are made from waste end up being more expensive to produce. So this is an opportunity for policy support. Use additional renewable electricity for e-fuels and for electricity that would be used to charge batteries. And so I covered this before on the importance of not taking existing renewable electricity and diverting it from another use. Use fully electric tugs and hovercraft and hybrid electric setups for cargo ships. So there's an opportunity here to electrify the tugs and the hovercraft that are going shorter distances or maybe even stay in port. And then you can also test out batteries for providing auxiliary power for cargo ships, avoiding emissions while they're near shore and at the port. And then also even for things like peak shaving. So if there's a sudden need to increase um, power for the ship. Instead of ramping up the engine, you can pull from the battery power. Use hydrogen made from additional renewable electricity for fuel cells to improve efficiency and virtually eliminate life cycle emissions. Not something I got into deeply in this presentation, but if you think about the from a greenhouse gas perspective, the least regrets pathway is to use renewable hydrogen directly in a fuel cell because you don't need to have a source of carbon. So some fuels like LNG, methanol, the diesel, all the different diesels, those are going to need a carbon source. And then for ammonia, you take nitrogen from the air. But if you use hydrogen directly in a fuel cell, and hydrogen is the renewable hydrogen is going to be the feedstock for all of these um, all of these new fuels that we're going to use to decarbonize the sector. If you can use it directly in a fuel cell, then you will have um, very low, if not zero, life cycle greenhouse gas emissions, and you'll also have no air pollution emissions. And one thing to keep in mind is that any of these fuels that we combust in an internal combustion engine, no matter how clean, even directly using hydrogen, are going to make nitrogen oxide air pollution emissions. So this would be the cleanest way forward. Big challenges here because you need to store either compressed or liquid hydrogen on board. The range is going to be more limited by using hydrogen because it's less energy dense per unit volume than other fuels. You need a new propulsion system in the form of a fuel cell, which is something that there is some experience with, but it's definitely not the default choice. You know, the default choice is put an engine in. So there's definitely some challenges, and then additionally the costs of the fuel. On the regulatory side, I think we just covered that quite well. Straightforward on air pollution. It all depends on the greenhouse gas side, how the regulations are developed, and what the calculated life cycle emissions are of the fuels that are being used, and the fuel and engine combinations in some cases like when you use LNG. And then safety regulations are still being developed. Last slide for you on the policy recommendations. So policymakers should focus on driving down the cost of producing and using low life cycle greenhouse gas e-fuels or making fossil fuels more expensive to close the price gap. Consider adding a low carbon fuel standard or a blending mandate that would apply to Great Lakes shipping. The blending mandate is how much of these low life cycle emission fuels you would need to be using over time in the system. expand the use of shore power and the availability of shore power that can be used to electrify tugs and harbor craft, and also to power cargo ships for their auxiliary power. We didn't find um, a good feasibility for fully electric large cargo ships, for example. Plan for new fuel storage infrastructure for hydrogen, ammonia, and methanol, which are the three fuels that are um, seem to have the lead in the global effort to decarbonize the shipping sector. Promote repowering and replacement of Great Lakes St. Lawrence Seaway vessels to make them zero emission vessels. There's some new funding that's available through the infrastructure spending that we have in the United States, at least, and that can be used for things like repower and replacement of hovercraft, as one example. And then our last one is to establish a public database of total annual fuel consumption and import fuel consumption by each ship in the Great Lakes St. Lawrence Seaway system. As part of this project, we developed an emissions inventory using satellite um, data from the ships. So we were able to identify the ships, see how fast they're going, and then use that information combined with some ship characteristics data that we have to try and estimate how much fuel is being consumed and how much um, carbon dioxide and other pollutants are being emitted. Um, that approach is well established. It's used by the International Maritime Organization for their emissions inventories. But what we have in the European Union, for example, is a requirement that the ships that call on European Union ports, either they're going to or from Europe, they have to report their fuel consumption and calculate their emissions for those voyages. And that ends up in a public database with the ship identification number, naming the ship. And then there's some calculations that are also reported on the carbon intensity of that ship for that year, and it's being used to understand what total emissions are from ships that are um, calling on European ports, and then the import fuel consumption part is being used to estimate how much shore power you would need to invest in to offset the fuel consumption that happens in ports. So it could be a useful way to get some real world data that's available that assists in policy making and policy decisions in the Great Lakes St. Lawrence Seaway system.